You know that feeling, right? When you're building something really amazing, fast, maybe even revolutionary, but then you hit this wall, this subtle nagging flaw. It's like, okay, you're training Mamba. It's super efficient, this new AI architecture. Lightning fast, yeah.
Yeah.
Even hangs with the big transformer models. But then you see it, it's kind of getting distracted. It just over-focuses on stuff, doesn't have that softmax thing Transformers use to quiet down the noise. And because of how it works, those important bits of info from way back get lost in the middle, all muddled up. It's so frustrating. So, okay, idea time. You think, I'll borrow that trick from differential transformers. You try subtracting, specific layers, the S6 layers, just like they subtract attention heads, and crickets. It totally flops, a real facepalm moment, because those S6 outputs, they aren't stable like softmax outlets. You can't just subtract them cleanly. It just, it breaks. But then, like, the light bulb goes on, that aha moment. You realize Mamba's secret sauce, it isn't just that S6 layer. No, it's the whole block, the convolution part, the gate, all of it working together. That's the key. So you build something new, Diff Mamba, differential Mamba. And this time, instead of just subtracting parts, you subtract the outputs of entire Mamba blocks running in parallel. And crucially, you add a normalization step afterwards. Got to rein in those wild, unbounded outputs, right? Make it stable. Plus, you tweak this little scaling thing, lambda, with a simple function, a sigmoid, just to keep the training nice and steady. Then you train it. You throw the usual suspects at a wiki text 8, inwik 8, standard language stuff. And what happens? Perplexity drops significantly. Lower perplexity means it's getting language better, predicting the next word more accurately. You make the models deeper, more layers, even better results. It's like the more noise the original Mamba might build up in deeper layers, the harder Diff Mamba pushes back against it. Then you test retrieval. Can it find info in super long text? You use Babylon benchmark and Diff Mamba. It crushes it. Seriously. Original Mamba starts to fade as the text gets longer, its performance drops. But Diff Mamba holds strong. Way better scores, especially in zero-shot tests. You even get fancy and peek inside the model's brain with this tool called Tune Lens. And the signal-to-noise ratio, much, much higher. Cleaner signals inside, especially in those early layers. Diff Mamba's ability to pinpoint that one crucial bit of info, the needle in the haystack, orders of magnitude sharper. It just sees it better. And when people say, oh, it's just a small tweak, you show them the internals. Look, it's cleaner, less noisy. Or they say, long context is niche. You point right at retrieval, at reasoning tasks, exactly the kind of stuff Mamba was built for. And Diff Mamba shines there. And that's when it really clicks. You didn't just patch up Mamba. You showed this whole differential design idea. It's not just a transformer thing. It's a fundamental way to make sequence models smarter. Smarter about what actually matters. Less noise, more signal. And that matters everywhere. Every token, every layer, no matter how long the text. Phew. Okay, so you heard the whirlwind tour of discovery there. Today we're diving deep into this fascinating world of differential Mamba. Our mission for this deep dive, really unpack how this new approach tackles some pretty tricky problems in large language models and why it's frankly a big deal for you, the learner, trying to keep up with the cutting edge of AI. So, expert, that whole thing I described, Mamba getting distracted by irrelevant stuff, can you ground that for us? What's the actual core problem there, and why is sorting it out so critical for these big AI models?
Yeah, that's a great way to frame it, that feeling of distraction. And what's fascinating is that this issue, what researchers call overallocation of attention to irrelevant context, it really is a fundamental challenge, especially for architectures like Mamba. It's not just some, minor technical quirk. It causes very real problems in large language models. Things like hallucinations where the model just makes stuff up confidently, or weaker performance on tasks needing long-range reasoning because it kind of loses track of important details from way back, and just generally it makes the models less robust. So yeah, making these models smarter about where they focus their internal attention, if you will, is absolutely critical to making them more reliable and capable. And today, we're gonna unpack the journey of differential Mamba. We'll see how it tries to fix these issues and potentially make LLMs much better, especially when dealing with long, complex streams of information.
Okay, let's definitely unpack that. So we hear a lot about Mamba, right? This exciting, super efficient alternative to transformers. Before we get into the fixes, can you just quickly remind us what makes it so fast and like the basics of how it works?
Sure. Mamba's made quite a splash recently. It's an efficient sequence model architecture built around these things called selective state space layers, or S6 layers for short. That's really its core identity. These S6 layers are the key to its speed advantage. They allow Mamba to process sequences with what's called subquadratic complexity. Basically, that means, unlike transformers, which get computationally very heavy as sequences get longer, Mamba scales much more gracefully. It can handle really long inputs much faster, often while achieving performance that's, in the same ballpark as Transformers. And how the S6 layer works, well, it uses these state space models, which are a concept from control theory, actually. It selectively processes the input signal, acting as a sort of implicit, efficient form of linear attention. It decides what information to keep and pass along in its internal state. But, and here's the catch we were just talking about, this design has some inherent vulnerabilities when it comes to noise or irrelevant context. Firstly, Mamba is softmax free. Transformers use softmax in their attention mechanism. You can think of softmax like a focusing lens. It takes all the attention scores and really amplifies the important ones while squashing the rest down towards zero. Mamba doesn't have that built-in mechanism to sharply suppress irrelevant stuff. And second, because it's state-based, it processes things sequentially. To understand the relationship between token 1 and token 1000, it has to kind of pass information through all the intermediate tokens, 2 through 999. This can sometimes lead to important earlier information getting diluted or dispersed among all the intervening potentially less relevant tokens. This combination creates what we call noisy intermediate representations, especially over long distances.
Right, okay. So super fast, efficient scaling, but potentially bit internally messy, especially compared to how Transformers use softmax to tidy up their attention scores. And that messiness, that noise, leads us straight to the inspiration for Diff Mamba, the differential transformer. How did that model try to clean things up? What was its clever trick?
Exactly. The noise issue isn't unique to Mamba. Transformers face it too, just maybe in a different way. The differential transformer from Ye and colleagues tackled this overallocation problem head-on within the transformer itself. Their clever trick was pretty elegant, actually. They took each attention head, you can imagine an attention head as like a specialized processing unit looking for certain patterns, and they split it into two parallel subheads. Then they computed two separate attention maps, basically two different views of what's important, and they literally just subtracted one map from the other. The idea was that the noise, being somewhat random or inconsistent, might cancel out, leaving a clearer signal. But a really crucial point that made this work well in Transformers. The outputs of the attention mechanism after the softmax are nicely behaved. They are probabilities, values between 0 and 1. They're normalized. So when you subtract them, the result stays within a predictable range. Everything's on the same scale, making the subtraction stable and meaningful.
Okay, that makes sense. Split the attention, subtract, and because softmax keeps everything neat and tidy between 0 and 1, the subtraction works. Simple, elegant. So here's where it gets really interesting, like you hinted at earlier. You've got this cool subtraction trick for Transformers. The obvious first thought is, hey, let's just do that to Mamba's S6 layers. Slap it on there. But that first attempt, which they call Diff S6, it just didn't work out. Why did that seemingly straightforward adaptation fail so badly?
It's that classic research story, isn't it? What seems obvious doesn't always pan out. The Diff S6 approach, applying subtraction just to the S6 layer outputs, it really underperformed. The hypothesis that emerged was that the S6 layer on its own might be a bit too simple, or maybe just not expressive enough to function like a full attention layer in this kind of differential setup. It wasn't capturing enough complexity for the subtraction to yield a meaningful improvement. But the really critical technical barrier was what we touched on before. Those S6 outputs are unnormalized and unbounded. They don't sit neatly between 0 and 1 like softmax outputs. They can be anything, positive or negative, potentially very large values. So trying to directly subtract these potentially wildly fluctuating, unbounded numbers, it led to instability. The training dynamics just went haywire. It wasn't a stable foundation for the differential trick.
Okay. So the S6 layer alone wasn't quite the right target, and more importantly, its raw outputs were just too unruly for simple subtraction. That failure must have been frustrating, but it led to that critical realization, the aha moment. The idea that Mamba's real power isn't just the S6, but the whole integrated block. How did that insight spark the actual Diff Mamba design?
Precisely. It was a setback that led to a breakthrough. Researchers connected this problem to some other recent work, particularly by Zimerman and others, which suggested looking at the entire Mamba block, the convolution, the gating mechanism, the S6 layer, all working together. The key insight was realizing that this whole block, as a unit, could be seen as creating something much richer, like an implicit attention matrix or a data-controlled linear operator. It's a more complex, expressive component than just the S6 layer in isolation. So the Diff Mamba architecture applies the differential idea at this higher level. It runs two parallel, full Mamba subblocks and subtracts their entire outputs. But critically, they knew they had to deal with those unbounded outputs. So the first absolutely essential addition was normalization. They added a normalization layer after the subtraction step. This is crucial to tame those potentially large output values and bring them back into a stable range for the rest of the network and for training. The second key addition was handling the lambda parameterization. Lambda is the factor that scales how much of the second block's output you subtract. Instead of some complex methods tried previously, they found that using a simple sigmoid function on the learnable parameter worked really well. It neatly ensures lambda stays positive and within a reasonable range, which again helps stabilize training significantly. And they didn't just stop at making it work, they made it efficient. A naive implementation would almost double the computation time, right? Running 2 Mamba blocks. But they cleverly parallelized it. They replicate the input across the channel dimension and process both paths within a single forward pass through slightly modified operations. This means Diff Mamba keeps roughly the same computational complexity, the same number of parameters, and the same memory usage as the original Mamba block. It's a smart implementation detail that makes it practical.
Wow, okay. So subtract the whole block, add normalization to clean up the mess afterwards, use a simple trick to keep the subtraction scale steady, and do it all efficiently so it's not way slower. That sounds like some clever engineering on top of the core idea. So, after all that careful design, the proof is in the pudding, right? What did it actually mean for performance? How did Diff Mamba compare to the standard, vanilla Mamba in real tests?
Right. Does it actually work better? And the results reported are pretty convincing. Across standard language modeling benchmarks, think Wikitext 103, Text8, and Wik8 Diff Mamba consistently outperformed the original Mamba. It achieved consistently lower loss, which means better perplexity scores predicting the next word more accurately or lower bits per byte, meaning it compresses information more effectively. To give you some numbers, for like a 12-layer model, they saw perplexity drop by about 0.4 points on Wikitext 103 compared to standard Mamba, and similar gains in bits per byte on Text8 and Wik8. Maybe sounds small, but in language modeling, those are solid improvements. And what's really interesting is this trend they observed. The benefits of Diff Mamba seem to become more pronounced as the models got deeper, as they added more layers. The thinking is that deeper layers handle more complex, longer-range dependencies, and that's exactly where the original Mamba's noise or overallocation problem might become more significant. So the differential approach has more impact there. Oh, and it also tended to converge faster during training, which is always nice. Likely because cleaning up that noise helps the model learn more efficiently.
Okay, better core language understanding, especially in deeper models and faster training, that's already pretty good. But what about that long context stuff, retrieval? That's supposed to be Mamba's home turf.
Absolutely. And that's where Diff Mamba really seemed to shine. They tested it on benchmarks like Babylon, which specifically measures how well models retrieve information from very long contexts. Diff Mamba consistently did better than vanilla Mamba, especially as the context lengths got longer. Its performance degraded much more slowly. The paper mentions ratio scores basically how much better it is than a baseline reaching up to 2.11 when fine-tuned, and even up to 3.5 in zero-shot settings for long context tasks. They also used another benchmark, long crawl 64. At medium scale, they found Diff Mamba's loss stayed pretty stable even as the context length increased significantly, whereas the original Mamba's loss started to climb noticeably. It just seems much more robust to very long sequences.
That's fantastic. Clear wins in language modeling, and even bigger wins in the long context retrieval tasks where Mamba is meant to excel. But, okay, playing devil's advocate here, how do we know it's really reducing noise? Could it just be that the extra parameters or the specific structure are helpful for some other reason? And what about those specific design choices? Was applying it to the full block really better than just the S6 layer? Was the normalization absolutely necessary? Did that specific lambda trick matter?
Excellent questions. Skepticism is healthy in research. The researchers anticipated this and did specific analyses to check. To tackle the "is it really reducing noise" question, they used that interpretability tool I mentioned, Tuned Lens. This tool allows you to sort of probe the internal representations at each layer of the model, and using it, they quantitatively measured the signal-to-noise ratio. They found that Diff Mamba consistently showed a higher signal-to-noise ratio compared to standard Mamba across most layers. The difference was particularly stark in the early layers. They even looked at how well the model could predict a specific needle token hidden in a long context. Diff Mamba's probability for that correct needle token was orders of magnitude higher than Mamba's. So yeah, direct evidence that it's producing cleaner, less noisy internal states. Then, for the design choices, they ran ablation studies. That's where you systematically remove or change one component at a time to isolate its effect. First, comparing diff Mamba, full block subtraction, against the initial diff S6 idea, just S6 subtraction. Diff Mamba significantly outperformed diff S6. That confirmed their aha moment. The whole block was indeed the right level to apply the differential idea. Second, normalization. They tested versions with and without that extra normalization layer after subtraction. The versions with normalization consistently performed better, yielding perplexity gains. This proved it was critical for stabilizing things, given Mamba's unbounded outputs. And finally, that lambda parameterization. They compared their simple sigmoid approach to a more complex reparameterization proposed in earlier work. Turns out, the complex version didn't actually give better performance. The simple sigmoid approach was just as good, validating their choice for simplicity and stability.
Okay, wow. So they didn't just show it works better, they actually looked inside to confirm the noise reduction and systematically proved that their key design choices, full block, normalization, simple lambda, were the right calls. That's really thorough. It really paints a picture of this not being just a random tweak, but a principled improvement. So what happened when they tried to scale this up? Did the benefits hold for bigger models? And what's the sort of the really big takeaway here about this differential design idea?
Good question about scaling. They did do some medium-scale experiments pre-training a 370 million parameter model on a large dataset, about 50 billion tokens from the pile. Interestingly, they found that the most effective setup at this scale wasn't purely diff Mamba blocks, but actually an alternation of standard Mamba blocks and diff Mamba blocks throughout the network. This mixed architecture seemed to get the best of both worlds, showing strong performance on general language modeling and excelling on long context tasks like long crawl 64. It suggests the benefits do translate to larger models, and that maybe selectively applying the differential mechanism is the most scalable approach. As for the big takeaway, I think it reinforces a really important point. The challenge of models getting distracted by irrelevant context, this overallocation issue, isn't just a transformer problem. It seems to be a more general challenge for sequence models. And diff Mamba provides strong empirical evidence, especially with that tuned lens noise analysis, that differential designs can act as a kind of noise-canceling mechanism. It offers a concrete strategy for improving signal clarity within these complex models.
So yeah, like we said at the start, they didn't just fix Mamba, they highlighted a potentially fundamental principle for making sequence models smarter, focusing their attention better, less noise, more signal. That feels really significant. But okay, even with all this success, no research is ever completely finished, right? What are the current limitations here? Where do the researchers themselves see this needing more work or heading next?
Absolutely, there are always next steps and open questions. One major area is developing a more rigorous theoretical understanding. While the empirical results are strong and the noise-canceling intuition makes sense, a formal mathematical framework explaining precisely why differential designs work so well for LLMs, whether Transformer or Mamba, is still kind of lacking. Another key limitation is scale. The experiments reported, while solid, are mostly at the small to medium scale, mainly due to, well, academic budget constraints, which is a common reality. Validating these findings on truly massive state-of-the-art scale models, those with billions or trillions of parameters, is a crucial next step for proving real-world impact. And finally, there's the question of domain applicability. Right now, this is focused on natural language processing. Can these differential design principles be effective in other areas where sequence models or similar architectures are used? Think computer vision, analyzing graph data, modeling time series. It's an open question whether this noise reduction approach translates effectively to those different kinds of data and tasks. Exploring that could be really fruitful.
Got it. So need more theory, need bigger scale tests, and need to see if it works beyond just language. Makes sense. Well, this has been a really fascinating deep dive into differential Mamba. We went from that initial researcher frustration through the clever insights and engineering fixes to seeing some really compelling results that suggest this is more than just a minor improvement. It feels like a genuine step forward in making AI models more focused and reliable.
I think so too. And if you zoom out, connect it to the bigger picture, this work on diff Mamba prompts a really interesting thought, doesn't it? It's not just about this one architecture. It asks, what if this core idea designing systems that explicitly learn to subtract noise and amplify the important signal becomes a more general principle? A fundamental tool for building intelligent systems that process sequences of any kind. Imagine the potential impact across AI if we could make every token, every layer, every context link, as you put it earlier, inherently smarter about filtering out the junk and focusing on what truly matters. It could be quite transformative.
That's a really powerful thought to end on. Making AI fundamentally smarter about signal versus noise. We hope this deep dive has given you, our listener, a much clearer picture of differential Mamba. and maybe spark some curiosity about where AI is headed. Keep exploring, keep learning, and we'll be back next time with another deep dive into the knowledge you need.